As we talk about arc length and polar coordinates, the arc length formula is very similar no matter which set you're in, if you're in parametric, polar, or regular. So I guess I should say if you're in a regular function, a parametric or a polar. So we have the integral from a to b, the square root of r squared plus dr over d theta, quantity squared with respect to r. So that's very similar to the arc length formula we used in functions, in parametrics, and now in polar. So what we're going to do is we're going to talk about how to use it. So let me get another screen here. So let's look at the length of the cardioid, and it says r equals 3 minus 3 cosine theta. So start off with the graph. This cardioid looks about like that. It's a sketch. It just gives you an idea what the graph looks like. Mine's not very pretty. The cardioid means it's an oval with a cusp. Sometimes a cusp, sometimes a loop in there. So there are a couple parts to this formula. The first piece is the r squared, and the second piece is the dr over d theta, quantity squared. So let's start with dr over d theta. So let's say dr over d theta and take the derivative here. And the derivative of 3 is 0, and the derivative of negative 3 cosine theta is positive 3 sine theta. And then we're going to square that. So dr over d theta, quantity squared, equals positive 9 sine squared theta. And then we're going to look at r squared. So we would write it twice and do FOIL. So we get 9 minus 18 cosine theta plus 9 cosine squared theta. So now we're going to look at our arc length. You need to check out your bounds for theta, but generally in polar it's going to be 0 to 2 pi, and it is in this case as well. So now we're going to start with r squared, which is 9 minus 18 cosine theta plus 9 cosine squared theta. And then we're going to add dr over d theta quantity squared, which is 9 sine squared theta. We have a d theta here. So let's factor out a 9. Let's not pull it all the way out. Let's leave it in there for now. But before we do that, let's talk about the fact that 0 to 2 pi can sometimes give us issues. So let's go from 0 to pi and use 2. So what we're going to do is we're going to use half this cardioid and double it. So 0 to pi, and we're going to double it. And then we have the square root of, let's take 9, parentheses 1, minus 2 cosine theta, plus cosine squared theta, plus sine squared theta, d theta. Now, I would like to take the square root of the 9, but let's leave it there for now. So we got L equals 2, the integral from 0 to pi. Now, when you look at this, this is an identity, cosine squared plus sine squared. Hopefully you see that that makes 1. So we're going to say 1 minus 2 cosine theta plus 1, and then we have our d theta on the outside. I have to go back to the pencil for that to work. So we have L equals 2, the integral from 0 to pi, the square root of 9, parentheses, 1 plus 1 makes 2, minus 2 cosine theta, d theta. All right, let's factor a 2 out of that. Let's see if we can make this work now. So L equals 2, the integral from 0 to pi, the square root of 9 times 2 is 18, parentheses 1 minus cosine, we don't have to write that 1. Let's not write that 1. So let's say 1 minus cosine theta, d theta. Does your brain ever do that? Because sometimes mine does, just like it did right there. Now, when we look at this, we need to look at our trig identities. We have a couple that might be helpful. The first one is we have 1/2 parentheses 1 minus cosine 2 theta equals cosine squared theta. And we could manipulate the left side to match this parentheses here. But I think it might be easier to look at the formula, the identity that says cosine of theta over 2 equals the square root of, oh, let's not use cosine, let's say sine. Sine of theta over 2 equals plus or minus 1 minus the cosine of theta all over 2. That looks very similar to what we have, we just don't have a 2. So I'm liking this identity more than the other one. I could see where you could go either way. I can happily explain it either way, but let's take the one on the right in this case, because we have a square root. And even if you had a square root to a power, let's say that you had this square root to the power of 3, so it would be 3 halves, and this would be to the power of 3 when you're done. Or if it was 5, then this would be to the power of 5. So there's a lot of what ifs in that what if board. But let's go back to that identity, and let's talk about the fact that, let's write it in here. Let's say note that we know that sine of theta over 2 equals the square root of 1 minus cosine of theta all over 2. Now that 2 is inside the square root. So if you think about that, I could do this. If I extended my square root, we could do this pretty easily. So let's go back to the problem and say L equals 2, the integral from 0 to pi. So let's make it a big square root. And right now we have 18 times 1 minus cosine theta, and it's over the number 1. But I would like to have a number 2 here. So I can do that by multiplying by 2. And what I do on the bottom, I, hopefully you said also do on the top. So L equals 2, the integral from 0 to pi. The square root of 18 times 2 is 36, parentheses 1 minus cosine of theta all over 2 d theta. Now I need to keep, if you look at this identity, oh, the screen is moving, hold that thought. So if you look at this identity here, I need to keep the 2 in the square root. So let's take the square root of 36 and pull this out to be a 6. So I'm going to move that to the front with the 2 to be a 12. So we have 12, the integral from 0 to pi. So we have the square root of 1 minus cosine theta all over 2 d theta. By the way, that matches this green note up here. Do you see that that matches exactly? So that is sine of theta over 2. So let's move this up. Let's say L equals 12, the integral from 0 to pi, sine of theta over 2 d theta. Now that was a pretty big jump. So the creative part is that multiplying by 2 on the top and in the bottom to make it look like what we needed to for the identity, that half angle identity that you never thought you'd see again. Okay, so now we're going to use, let's let u equal theta over 2. We're going to do some nice pretty calculus. So this is the same thing as 1/2 theta. The derivative of that is 1/2 d theta. So d theta is 2 du. So we've got 12, the integral from 0 to pi, sine of u times 2 du. So we got 12 times 2. Let's go ahead and put that there and say 24. Well, let's clean it up, make it pretty. So we have 24. And the integral of sine of u is negative cosine of u. Yep. From 0 to pi. So that means we have negative 24 cosine of, now u is theta over 2 from 0 to pi. So we have negative 24 cosine of pi over 2 plus 24 cosine of 0. Now cosine of pi over 2 is 0 plus 24 times cosine of 0 is 1. So this answer is 24. So I'm not real sure what we needed here, but I think it was that magic identity in the middle. Let me show you how to do the other identity the other way in just a minute, okay? So let's do that on the next screen. Remember that inside the integral we had the square root of 18. I should go back and pull it, parentheses 1 minus cosine of theta d theta. So there was a 2 out here. So what we did was we used the one identity, but let's talk about the other identity because some people prefer, then you have options. Let's go with it that way. Then you have options. I like the half angle identity. I think it's pretty. So let's start with this one. It says 1/2 1 minus cosine 2 theta equals cosine squared theta. So what you have to realize here is we need a theta to be here. This takes a little bit of creativity, which is really fun. So we have cosine of 2, but I need that 2 to go away. How do you get a 2 to go away? All you can do is multiply. So what we want to do is we multiply by 1/2. So we're going to put in here 1/2 theta instead of theta equals, now what you do on one side, you also do to the other. So we're going to change out this theta for 1/2 theta. Does that make sense? We replace the theta with the 1/2 theta. Now look at the fact that the 2 and the 1/2 are going to cancel to just give me a theta. Isn't that pretty? So let's go back to, we have 1/2 parentheses 1 minus cosine. Now we have just a theta there equals cosine squared. Let's call this theta over 2. Now this matches the parentheses here, but I got a 1/2 out front and I need to get rid of that. So again, how do you get rid of a 1/2? You can multiply. So we're going to multiply both sides by 2. So then we have the 1 minus the quantity of 1 minus cosine of theta equals 2 times cosine squared theta over 2. Now this is a true statement. This parentheses right here equals the value on the right-hand side. So you could go back to your integral and say the integral from the 2 times the integral from 0 to pi. And we have the square root of 18 times, now instead of that 1 minus cosine theta, we're going to say 2 times cosine squared of theta over 2 d theta. Now 18 times 2 is 36, and the square root of that is 6. So again, we're going to do this magic and say 12, the integral from 0 to pi. And we have the square root of cosine squared of theta over 2 d theta. Now the squared and the square root cancel. So we have 12 times the integral from 0 to pi, and we just have cosine squared. Nope, no squared. The squared canceled with the square root. So we have cosine of theta over 2 d theta. And it's u sub, and the problem finishes the same. So you can use either of those identities that you want to go from there. And hopefully that makes sense. I know I only did one arc length, but if we go back to the beginning, the key is to figure out what your r is, to find dr over d theta, to square them both, and to have the correct bounds, because it's your arc length formula that you're using. I think the hard part is this, the identities that you have to use in the middle of this one. Well, have a great day, and let me know if you have any questions.